Hi there, and welcome to my talk on the paper Improving Robotic Grasping on Monocular Images via Multitask Learning and Positional Loss, accepted at this ICPR conference. My name is William Prew, and I'm the lead author on this paper, which is work towards my PhD thesis, along with my supervisors and co-authors, Toby Breckon, Magnus Bordewich, and Ulrich Beierholm. This paper contributes towards improving data-driven approaches towards robotic grasping using computer vision models. This work is used in piloting robotic grasping policies like the setup of my rubber arm here that I have in the visualization laboratory in the computer science department. This is just an example of the trained network working in action. It produces grasps using only monocular RGB inputs and is capable of picking up a large variety of objects, including the small 3D printed object shown here by proposing a single planar grasp. This is carried out using our Bordewich robotic arm, which I have also programmed as part of my PhD, and this is a low-cost robotic arm capable of picking up small payloads, but the model can also be scaled for use with larger and more precise arms, such as the KUKA arm used in experiments at Google. Multitask learning has previously been shown to improve performance in other areas of machine learning, and has even crossed over into earlier robotic grasping work by performing concurrent tasks such as classification during object grasping. However, this is typically time-consuming to label large datasets and is therefore restricted to smaller datasets such as office stationery or in papers where they find objects lying around, such as tools. We wanted to investigate whether grasping success would improve in a similar manner with data easily accessible to large-scale datasets. The network used in the current paper is a typical convolutional neural network that uses the MTG-CNN backbone in a recent paper by Morrison and colleagues. The first contribution of this paper is replicating the second half of this network to allow for the concurrent learning of a similar auxiliary task. This is represented in the presentation as the Step 3 construction task, as this data is typically readily available to large-scale datasets and therefore features a large amount of work on reproducing disparity maps from monocular images. This network was then trained on the large-scale Jacquard grasping dataset, which is a large data set with a very large amount of correctly labeled grasps for a wide variety of objects, featuring grasp position in pixels and a corresponding grasp angle and required gripper width, all verified in a simulated setting. This is then transferred into a set of images that we use to train the network, produce a grasp at each pixel of an image, and therefore produces an associated probability of success for each grasp. The grasp positions are changed into a probability map, and the angle is further decomposed into two unit vectors, cosine and sine, that can be used to produce a grasp angle later between negative pi over 2 and pi over 2 to help train the network as per the MTG-CNN model and the reference to Hara et al. Here. The grasp angle becomes symmetrical outside of these 2 points. Grasps are then calculated during post-processing and can suggest a number of correct grasps given the requirements of the task. The figure shows examples of direct outputs from the network, including example depth map from a monocular image. The best grasp center is proposed where the network predicts the pixel that has the highest probability of executing a grasp. The corresponding angle and gripper width for that pixel are then taken to form the rest of the grasp. The sine and cosine angle images from the output of the network are combined using the above equation to reform the required grasp angle between negative pi over 2 and pi over 2. The second contribution of our paper is this new loss function that we introduce, and modifies the already existing MSE loss using the MTG-CNN paper, and scales the angle and the width outputs by the ground truth grasp probability from the Jacquard dataset. The motivation for this is that this encourages the network to learn at points where information is centered around the grasps only, and where a grasp is likely to occur, and therefore reduces the time spent learning about relevant background information. This speeds up the rate at which the network learns about successful grasps over non-successful grasps. This can be seen during training, as the performance on our test set is significantly improved in the earlier epochs. Therefore, we can infer from these grasps that the positional loss function requires less data before reaching optimal performance with each network. Here we count a successful grasp by measuring the intersection over union for the grasp proposed and the nearest grasp rectangle from the Jacquard dataset. For a successful grasp to be counted, the intersection over union, or IOU, must have over 80% overlap with the ground truth, and the grasp angle must be within 15 degrees to be counted as successful as per the Jacquard dataset metrics. We trained 6 models in total on 5 different splits of the Jacquard dataset, And the table here shows their average performance on the same validation set with standard deviation included. All models were trained with only monocular RGB input. The 3 models included the original MTG-CNN model, the multitask grasping network trained with 2 different auxiliary tasks, saliency prediction and depth reconstruction. All 3 models were then trained with and without the positional loss function included as per the previous slide. As we can see from the final results, the positional loss function provided little benefit to the final results, but depth reconstruction provided the greatest benefit to grasping performance as this produced the best average performance across all models. This suggests that the depth reconstruction provides some crucial understanding to the grasp success in the earlier shared parts of the network, and that the original network trained only on RGB input could not infer alone that may be useful in training models with impoverished data in future. Thanks for watching my brief overview of our paper, and enjoy the rest of the conference. Links to the papers referenced here are included in this slide.